So question 120, B and C, gives you the structure of formaldehyde and is asking you a couple things about the atomic orbitals that are used to create some bonds. So first, they're asking you to identify the atomic orbitals that form the carbon to hydrogen bond, so those bonds right there. And you get those bonds when orbitals overlap. Now, so in order to draw those orbitals overlapping, we have to figure out what type of orbitals we even have. So first, hydrogen. Now, hydrogen only has an s orbital. It only has one electron, and so it doesn't even fill up this one orbital. If you remember, orbitals are places where electrons fly. Electrons are like little magnets that have a north and a south end. And so you could have two electrons pair up with each other, the south end on one and pairing up with the north end on the other. And so two electrons can fly really close together in these orbitals. But it's only after you get two electrons in an orbital that electrons have to fly in a different way. Because if you try to take another electron, and it doesn't matter how its little magnetic arrangement is, if you try to put this in here, it's going to be repelled by one of the electrons that are already there, because the north and south ends would line up. And if I had drawn it the other way, so it was upside down, then it would have repelled it would have been repelled by the other electron. So you can fit two electrons in the same sort of space in an orbital because their little magnets will line up with each other and be okay, but you can't fit a third electron in. And so this third electron would have to start flying in a new space or a new orbital. And sometimes that would be like a p orbital or something like that. But if you only have one electron, like hydrogen has, then there's no reason for this hydrogen to have a p orbital. Its electron can fly around in that s orbital, that lower energy orbital, just fine. And so hydrogen only has an s orbital. It only has that sphere there. So I'm going to draw these orbitals in green. So hydrogen, here let me make it just a little darker. So hydrogen has an s orbital. So this hydrogen here I'm going to represent with this sphere orbital. And the other hydrogen also has only an s orbital. So that hydrogen I'm going to represent by that orbital. Okay, so much for the hydrogens. They only have one electron, so that electron flies around in the lowest energy orbital, the s orbital. Carbon has a whole bunch of electrons, so it not only has the s orbitals, but also the p orbitals. And depending on how many pi bonds a carbon has, it will mix the rest of its s and p orbitals in the way that we saw in the problems in the previous two exercises, so 123, and especially when we first went over it in 122. So, this carbon here has one sigma bond, two sigma bonds, and three sigma bonds. Remember, a sigma bond is the first bond you ever form between two elements. And every bond after that, so the second bond between this carbon and hydrogen is going to be a pi bond. So this carbon has one pi bond. That means it's sp2 hybridized, because it has an s orbital and three p orbitals to work with. You need a p orbital in order to form this pi bond, so you only have an s and two p's to mix together, and so you get sp2 orbitals. Now when you mix those together, you get orbitals that look like something Frankenstein orbitals that look like something kind of in between. So they're 2/3 p, and so they still have that sort of peanut shape, but one of the lobes in the p, so like one of these lobes, gets fatter because that's where the s added. And so these here are your sp2 orbitals. Now they repel each other, and they repel each other until they get as far apart as possible, and so they form a sort of triangle. Now I'm going to put draw each of these in a different color so that it doesn't mix together as much. You'll see what I mean. So I'll have one sp2 orbital. So this is the carbon right there. I'm going to draw the orbitals on it. So we've got this one sp2 orbital. And we're going to, so that would be like this one. And then we're going to have another sp2 orbital. So here again is the carbon in the middle. That's the smaller lobe. Here's the larger lobe. So that's our second sp2 orbital. And then you'd have a third sp2 orbital. So here our carbon is, have the little end of the lobe, the longer end of the lobe. And so that would be like our third sp2 orbital. And notice they get as far apart from each other as possible, 120 degrees, like in a triangle. So that's the orbitals that has. And you can see you have overlap. Excuse me, you have some overlap here. Highlight this in orange. Oops, this. So you've got overlap here. That's a bond. You have overlap here. That's another bond. Those overlaps are what give rise to these bonds right here. So this bond is being created by the overlap of an s orbital on the hydrogen and an sp2 orbital from the carbon. So those are the atomic orbitals that form the carbon to hydrogen bond on the left. And if you look on the right, you'll see the same thing. You have an s orbital from the hydrogen overlapping with another sp2 orbital from the carbon. So the orbitals that overlap to form these carbon to hydrogen bonds, really the overlapped area there, are an s orbital from hydrogen and an sp2 orbital from the carbon. And you get that overlap twice. Now, if you're looking at this, we did omit to talk about one thing, which was the oxygen at the top. We never thought about the orbitals there, or how that fits into there, or how the bonds are forming between the carbon and the oxygen. So you find the hybridization of any atom the same way. You look at the number of pi bonds that it has. And if you zoom in to this oxygen, then you would notice that it has one sigma bond. That's the first bond you ever form between two atoms. And it has one pi bond. Every bond after the first bond is a pi bond. So because it has just one pi bond, the hybridization for that oxygen is going to be sp2. Anytime you have just one pi bond, any atom that has just one pi bond is sp2. Because it needs to set one of those three p orbitals aside to form the pi bond, and so it can only mix the other two together with the s orbital. So oxygen would actually look a lot like this carbon here. It would have one sp2 orbital coming down to form the sigma bond, and the two lone pairs, each lone pair would also exist in an sp2 orbital. So little lobe, big lobe. So with carbon, two of the sp2 orbitals were going to form bonds. But in this oxygen, two of the sp2 orbitals are going to be the places where the lone pairs are flying around. So because oxygen is sp2, it's also going to have these three orbitals. Let's flip this around. These three orbitals. Of course, it won't have the hydrogens, the s orbitals from the hydrogens, and it won't have those bonds. But it will still have those three sp2 orbitals where they overlap with the sp2 orbitals from the carbon. You get the sigma bond there. So this overlap here is the sigma bond, the first bond that we formed between the carbon and the oxygen. And then the lone pairs, each lone pair would exist in an sp2 hybridized orbital. And so that is what we've got. So we've got oxygen here at the top. We've drawn the sigma bond between the oxygen and the carbon, which we have at this lobe there. So this is oxygen-carbon. We have the two bonds from carbon to hydrogen, and we've drawn the orbitals between those. And we have the two lone pairs, each existing in an sp2 orbital. So what type of atomic orbitals do the lone pairs on this oxygen occupy? They occupy sp2 orbitals, these s orbitals right there. And you would know that because that oxygen only has one pi bond, and so it's sp2 hybridized. Now, just for your own, so that would be the solution for that. Just for your own curiosity, you may be wondering, how about the pi bond? Like, okay, so we explained each of these sigma bonds. This is an s and an sp2 overlap, s and sp2 overlap. This is the overlap from an sp2 orbital on both oxygen and carbon. But how do you get this pi bond? Well, remember, you get pi bonds from the overlap of p orbitals. So if we take these, so if we take this and we look at it from the side, if this were in a plane, the p orbitals would be perpendicular to this. So you'd have a p orbital coming up and going down, a p on the oxygen, and a p orbital going up and going down on the carbon. And really, I should have drawn those as a little fatter because it's the overlap between those p orbitals that causes the pi bond. So that would be that second bond between the carbon and the oxygen. So it takes a little bit of mental acrobatics to visualize these things, but you form bonds by the overlap of orbitals, and you can figure out the orbitals on any atom based on the number of pi bonds it has. And lone pairs exist in those orbitals that you predict that way.